From ancient sailors tying ropes at sea to the complex patterns hidden within nature, knots have always been more than just practical tools. They are deep mathematical puzzles. In modern science, we study these structures through an advanced branch of geometry called topology. By analyzing their paths, we can assign specific numerical values to them, or even use algebraic equations like the famous Jones polynomial to understand their behavior. This isn't just pure math. It actually helps us unlock the secrets of biological structures, like the knotting of DNA strands. But to understand how this works, we must first ask a fundamental question. What exactly is a mathematical knot? Think of it as a single continuous loop that is closed with no loose ends. If it has no crossings at all, we call it the unknot, the simplest possible loop. But once we start twisting and weaving the loop around itself, we create entirely new structures. Even if a loop looks incredibly tangled, it might still just be a disguised version of the unknot. To study them clearly, we project these three-dimensional curves onto a flat, two-dimensional plane. This is what we call a knot diagram. Imagine shining a light on a 3D knot. The shadow it casts on the floor gives us all the topological data we need. Here are the most classical examples: the unknot with 0 crossings, the trefoil knot with 3, and the figure 8 knot with 4. Now, how do we know if two complicated diagrams represent the exact same knot? We use what we call ambient isotopy. This relation is mathematically strict, meaning it satisfies the reflexive, symmetric, and transitive properties. This allows us to dynamically deform, stretch, or untangle a knot without cutting the strand. And according to topology, any such deformation can be broken down into just 3 basic steps, known as the 3 Reidemeister moves. The first move, R1, allows us to simply twist or untwist a single strand. The second move, R2, allows us to slide one strand completely over or off another, adding or removing 2 crossings. And the third move, R3, lets us slide a strand across an existing crossing, changing the layout without changing the knot itself. In conclusion, 2 diagrams represent the exact same knot, if and only if we can transform one into the other using a sequence of these 3 simple moves.